Welcome back to our video module on quantum mechanics. In our previous video module, we looked at separating the general form of the wave equation into an x-dependent solution and a t-dependent solution. When we did that, we found that the potential profile of the system really dictated the types of solutions we're going to see. So what I've done here is I've drawn a potential well. The height of the potential right here is infinity, and down here we're going to say it's 0. Likewise, in the x direction, the origin is going to be in the bottom left, and the potential will go back up to infinity at A. My question for you is, what types of solutions can we expect to see in this simple potential profile? Today, we're going to be playing with the time-independent Schrodinger's equations, identifying solutions in an infinite square well, and try to understand more generally how to approach problems like this. So first off, we already know phi of t. We already know the general form of the solution for the time-dependent function. The only thing that remains is identifying the form of the x-dependent function. Well, let's start with the time-independent Schrodinger equation and see what we can figure out. First, let's look in the areas where the potential is infinity, which means the only way both sides of these are going to be equal is if the wave function goes to 0. So if we wanted to graph the wave function, we know that in areas where the potential is infinity, the solution is 0. And we could have figured that out just by intuitively looking at this, saying, well, if the potential is infinity, is there any way that a wave can be in that space? It's like there's this infinite force or this infinite barrier pushing the wave into this area. And we could write this solution as just saying c of x equals 0, where the potential equals infinity. Now in the middle area is where it gets a little bit more fun. In this case, we know the potential equals 0. So let's go back to our time-independent Schrodinger equation, and we'd see that v is going to go to 0, which means this whole term is going to go to 0, leaving us with a second derivative is some function of the function itself. So we know that c is going to be of the form of sine of x. So that might look like, let's just do half of a sine wave right here. That might be one solution. One can imagine if the e was higher, that's going to lead to a different coefficient in here, which might lead to a different solution in red. As a matter of fact, there's an infinite number of these solutions, depending on what E is, or depending what the total energy is. And if we wanted to write out what the solution of the wave function is when v equals 0, we know it'll be some function of sine. Obviously, the other constants like E and h bar squared over 2m are going to help us identify particular solutions. We call this setup an infinite square well for obvious reasons, and I hope this quick video has given you a feel of how to use the time-independent Schrodinger equation and the potential profile to identify the general form of possible solutions. Join us in our next video as we put a little bit more teeth on this and play with this concept a little more.